This is the video for section 7.2 notes, slides 10 through 13. All right, so first thing we're talking about is a partition. All right, so a partition is just a division of a particular interval. So we have this interval from 1 to 4, and we've created this partition, basically, is just dividing the interval up. All right, now the norm of the partition, which is given by this symbol, it looks like absolute value, but it's two bars on each side of this P, and that refers to the largest interval within the partition. All right, so if I look at this, we see that 1 to 1.7, that's a distance of zero point 0.7. 1.7 to 2.3, that's a distance of zero point 0.6. 2.3 to 3.5, that's a distance of 1.2. And 3.5 to 4, that's a distance of zero point 0.5. So the norm of the partition is the largest of those sub intervals, right? So 1.2 is the norm of the partition. Not a big deal right here, but we do use the norm of the partition in a later thing that we want to make sure we understand what that refers to. All right. Now, next thing we're going to do is we're going to use this partition to provide an estimate of the area under the curve. All right. So now we have this curve x squared plus 2. All right. And so we have this graph that looks like this, and we are trying to estimate the area under the curve from 1 to 4, right? All right. So now we're going to take the partition given here, 1 to 1.7, right? So then there's a point. Now I'm going to zoom in on that a little bit. Okay. So let me create a larger picture here. So, all right. So here's 1 and here's 4. All right. So I'm going to go from 1 to 1.7, right? Okay. And then I'm going to go from 1.7 to 2.3. Right? So that's a wider, sorry, not much wider. Let me redo that. 1 to 1.7 is about here. 1.7 to 2.3 is about here. Then I have 2.3 to 3.5, a much wider one, and then 3.5 to 4, right? Okay, so now it says we're going to use this partition to estimate the area under the curve using a left-hand endpoint. All right, so in between the first two, 1 and 1.7, we're going to use the left-hand endpoint. So the left endpoint is going to represent the height of this rectangle. Okay. Then the next one, we're going to go from 1.7 to 2.3, and we're going to use the left endpoint to represent that height. Then the next one, 2.3 to 3.5, we're going to use the left side to represent that height. And then from 3.5 to 4, we're going to use the left side to represent that height. All right. So we're taking the width of zero point 0.7 times the height, which would be f of 1, right? The left-hand endpoint. Plus, the next width is zero point 0.6 wide times the height, which would be f of 1.7. All right, and then plus the next width is 1.2 times a width of, well, the left-hand endpoint there is f of 2.3. And then lastly, the last one is zero point 0.5 wide times a width of f of 3.5. All right, so now remember f of 1, f of 1.7, we're just plugging into that original function x squared plus 2. So I have zero point 0.7 times 1 squared plus 2 plus zero point 0.6 times, the next one would be 1.7 squared plus 2 plus 1.2 times 2.3 squared plus 2. And lastly, zero point 0.5 times 3.5 squared plus 2, right? So now we're getting the area of each one of those. All right, so I'm going to do this calculation. So 1 squared plus 2 is 3 times zero point 0.7, which is going to give us 2.1. Right, so we have 2.1, which represents the area of this rectangle. All right, then I have plus, now I'm taking 1.7 squared plus 2. All right, and then I'm going to multiply that by zero point 0.6, which is going to give us 2.934. Plus, now I have 2.3 squared plus 2, and then times 1.2. All right, and that gets me 8.748. All right, so remember this is like the 2.934. All right, and then this one is 8.748. And then this last one is found by taking zero point 0.5 times 3.5 plus 2. So 3.5 squared plus 2, and then that times zero point 0.5. And we get a value of 7 7.125. So 7.125. And then that is representing this area. And so this is the left-hand endpoint, right? We're going to add all those together, right? So I have 7.125 plus 8.748. And of course, you should be able to do this calculation pretty simple. 2.934 and then plus 2.1, right? So together, this gives us 20.907, which would be our estimate of the area under this curve, all right, using a left-hand endpoint. Okay, now, okay, what we're going to learn is that when we use a rectangle to represent the area, we are going to refer to this as a Riemann sum. And so what we can do is we can refer to this as a left-hand Riemann sum. All right, so this is a left-hand Riemann sum. Now, we could always use a right-hand Riemann sum as well, and that would be by using the right-hand endpoints. Okay, so that is slide number 10. All right, now slide 11. All right, we're going to do basically the same thing now. It says you and a companion are driving along a twisty stretch of dirt road in a car whose speedometer works, but odometer is broken. To find out how long this particular stretch of road is, you record the car's velocity at 10-second intervals, right? So 0, 10, 20, 30, 40, 50, 60. All right. With the results shown in the table. All right, so we have time and velocity. So now, by using the left-hand endpoint and 6 subintervals, not 12, I edited the table, all right, and 6 subintervals of equal length. All right, so we have 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60, right? And now we're using a left-hand endpoint, so that means we're doing a left-hand Riemann sum. Okay. All right, so now how wide is the first interval? Well, it's 10 units wide. And what is the left-hand value? It's 0. Plus, the next one is 10 to 20. That's 10 units wide times the left-hand value is 44. Plus, the next one, 10 wide times the left-hand value of 15. Plus, 10 times 15, right? I apologize. Plus, the next one is 10 wide times the left-hand value of 35. Plus the next one is 10 wide by the left-hand value of 30. And then the last one is 10 wide by the left-hand value of 44. So now you'll notice that this 35 never gets used because it is not the left-hand value in any of those intervals. Okay. So now obviously this one's pretty easy, right? We're just adding together those and multiplying, right? So 44, sorry. All right, so 44 plus 15 plus 35 plus 30 plus 44, right? Which gives us 168, and then times 10, of course, so we get 1680 what? Well, what did we do? We multiplied feet per second times seconds, right? So this is an amount of feet. So this is how far the car has traveled during that 60-second interval. All right. Now, the next one by using right-hand endpoints. So now we're not going to use the first one because the first one is not the right-hand value. Okay, but the last one is a right-hand value, right? And so now we're going from 0 to 10 times 44. So we're saying 10 times 44 plus 10 times 15 plus 10 times 35 plus 10 times 30 plus 10 times 44 and then plus 10 times 35, right? So this is basically the same, except now I've added on this 35 and I did not add on the 0 at the beginning, right? So really now all I'm doing is just adding an additional uh, 350 onto that. So now this one gives me 2,030 feet. Okay. All right. So that is left hand and right hand Riemann sum. Remember, a Riemann sum is when we use a rectangle to estimate the area under a curve. All right. So let's keep going here. All right, so now on to slide number 12. All right, now we also can use a trapezoidal sum, right, or a trapezoidal rule. But the trapezoidal sum is really just the average of the left hand and the right hand endpoints. All right, and so how would I find a trapezoid? Well, if you take each of these, right, the area of a trapezoid is 1/2 base 1 plus base 2 times the height, right? Now, the height is actually the horizontal distance, right? So this is the height of each of these, right? And so how is this actually the average of the two? Well, if you distribute the h, I have b1 times h plus b2 times h, and then take half of that. So, right, it's the average of those two things. So remember, B1 is going to be the left hand, and B2 would be the right hand, and the height would be this width, right? And so if I find the area of this trapezoid, I'm actually just finding the average of the left hand and right hand Riemann sums. Okay. And so that's really it for slide 12, but it is possible that you're asked for a trapezoidal sum. Okay. All right, so now moving on to slide 13, okay? The following table shows the speed of a runner taken every half of a second. Estimate the distance the runner went. All right, so remember we've got speed in feet per second and time in seconds. All right, and so it says use the trapezoidal rule and the 4 sub intervals, right? We only have 4. I changed the table. All right, so trapezoidal rule, right? So we're going to take the width of the two, so that'd be a width of 0.5, right? Okay, and remember, the trapezoidal sum is 1/2 of base 1 plus base 2 times the height. Now, remember, the height represents the horizontal width of the interval. All right. So we're going from 0 to 0.5. So that is, we're going to take 1/2 base 1. The height on the left is 0 plus the height on the right is 6.2 times the width of the interval is 0.5. All right. Plus half of. Okay, now we have 6.2 to 10.8. All right, and then times the width of 0.5. Remember, 0.5 to 1. All right, the next one, 1/2. Okay, now I have 10.8 to 14.9. All right, and then times the width of 0.5. And then lastly, I'm going from 1.5 to 2. So we take 1/2 the height of 14.9, not 14.8, sorry, 14.9 plus 18.1 times a width of 0.5. All right, and so now we have our trapezoidal sum. Now, obviously, you should be able to do this calculation. All right, so I have 0.5 times 6.2 times 0.5. All right, and that's going to get me 1.625 plus. All right, now I have 0.5 times 6.2 plus 10.8. And then we're going to multiply that by 0.5 as well. So let me do this calculation. 6.2 plus 10.8, and then times an additional 0.5. All right, so that's going to get us 4.25 plus, and then I have 0.5 times 10.8 plus 14.9 times 0.5. All right, that's going to get me an additional 6.425. And then the last one, I've got zero point 0.5 times 14.9 plus 18.1, and then times the other zero point 0.5. All right, and so that gets me 8.25. And so then I'm going to add all of those together. So 8.25 plus 1.625 plus 4.25 plus 6.425, and that gets me 20.55. All right. So now the last one, midpoint Riemann sum with 2 subintervals. So now midpoint means I'm going to go from 0 to 1, and I'm going to take the middle point between those two. So 0 to 1 is a width of 1 times the middle point is 6.2. And then I'm going from 1 to 2, and the middle point is 14.9. So width of 1 times 14.9. All right, so 6.2 plus 14.9. and that gets me 21.1. So that is a midpoint Riemann sum. So midpoint Riemann sum is important. You have to skip over one and then use that one in the middle. All right, so that is slide number